Okay, thank you very much, Kundan, for your nice introduction. So, the series of lecture in this program, uh, from the beginning, if we'll see, Professor Kothari has introduced the concept of microgrid along with the structure of power system in India and as well as abroad also. And also he has described the benefits and also benefits of the renewables, especially why renewable is so attracted. He has defined very much about though nuclear is clean, even if it is not disposable, so it is difficult to dispose the nuclear byproducts. So therefore, most preferable nowadays is solar and wind. Though yesterday also Dr. Siva Subramanian has clarified this, and also he talked about the demand side management more. And today we'll see the microgrid stability, control, and protection. So because these are very vast areas, stability, control, and protection. First of all, I will introduce microgrid because I thought with proper definition, nobody has till now defined microgrid. I will define, then we'll talk about stability, then some case studies, along with that some control aspects, and I'll just give an introduction to protection, and one more session will be there on protection. Also, after these lectures, you will see nowadays people are moving towards more towards the artificial intelligence application and machine learning application in protection and control. So we'll see a little bit towards that. So let me start my presentation. In the stability aspect, mostly we'll cover the small signal stability. Why small signal stability? Because uh, small signal stability, if you are a power system person, you must be knowing small signal stability is because of the small disturbance, but sometimes it causes a chaotic condition, creating sometimes blackout as well, right? So therefore, so we'll start now. We'll start with stability, then little with control aspect, then protection. So my presentation layout is like this. We'll have little bit introduction, then classification and architectures of microgrid, which I think nobody has covered. I will tell briefly, and then stability aspects of microgrid. What is the stability aspects? Then we'll talk about a detailed small signal stability analysis and a case study. Then I'll talk about little bit introduction to the protection. In another lecture, a little more will be covered, and then we'll conclude, summarize the talk. So if we'll see this diagram, we can see here, this is a classical system, vertically integrated utility, right? Where generation, transmission, distribution, they're combined together and they're in a single utility. It is managed, operated by a single utility, right? And gradually what happened after 80s, during 80s, gradually the disintegration took place between generation, transmission, distribution, saying that it will give us more competition and more reliability to the system. So therefore, disintegration started early in the 80s. During 80s, Chile started first in the South America, and gradually other countries adopted. Though it has certain disadvantages, but still people have adopted. Now it is going on disintegration of the system, whole system, and also gradually the disintegration took place in the generation side, where different generating companies participate in the system market, and people have their, or discos have their own choice to buy from particular generating company. Then transmission obviously remained monopoly because we cannot put multiple transmission lines in a system. So therefore, it will remain always monopoly, and it is also remain monopoly. So again, in the distribution side, we have also disintegration took place where many discos participate, and the customer or the consumer has a choice to buy from a particular disco. It doesn't happen now in India, but still in India, the Odisha is the first state where this privatization happened, where the private participation happened. The discos participate in the market, and but still the consumer has no choice to from where to buy the electricity. It may happen in future scenario. Let us see. Now the structure looks like this. So in the Genco we have a wholesale competition and Transco remains monopoly. In India it is with the Power Grid Corporation PGCL, which is looking after it, and also PGCL has segregated into two companies. One is Poshoco and other one is PGCL remained. So Poshoco is looking after the operational aspects, the security aspect, and it is acting as the system operator. Uh, and in Disco, many participation. So here retail competition is occurring, and here now with this scenario, with a huge competition, and as per the standardization of the reduction of carbon footprint, many more complications. So can we achieve the target of reliability in the whole system? It is very difficult. So therefore, gradually, there are most of the losses happen in the T&D. So that is also one of the aspect. If your generator is centralized, it is located somewhere very far from the load center, obviously losses are more along with the theft, right? Therefore, it is always preferable if your generator is near to the load center. Huh? And people will buy from the generator, and it is easy, and also loss will be reduced, voltage regulation will be maintained, right? So because of this aspect, and also the renewables can be put in modular size, it can be put near to the load centers very easily, right? So that is one of the aspects. Now considering these aspects, the concept of intelligent grid, as Professor Kothari mentioned, previously it was known as intelligent grid, came into picture where considering all kinds of distributed generators along with the renewables, how we can make intelligent grid. Later on it was named as smart grid, right? So we can see these corners where the objectives are very well mentioned of the smart grid. The objectives of smart grid are: one is energy security, that is very essential for consumers as well as the utilities. It is very essential. Then demand side management, it is also very essential in order to make the system more reliable and also reduce the losses in the system, right? Then this is most important, greenhouse gas reduction, and obviously it is the use of information technology and communication through which it will happen. So these are the smart grid components we can see here. Here it is conventional power plant. This is a microgrid which is connected, right? Electric vehicles. So they all can interact with one another. So we call this intelligent grid. They can interact and they can make the system more reliable. Okay. So this is taken from this publication, and smart grid is cyber physical system perspective, right? So, so what are the benefits to the consumers when the system becomes smart? So it can monitor their energy consumption in real time. Why it is essential? This monitoring of energy in the real time, because as the system becomes competitive, so there are different prices offered in the market. So if we'll monitor the consumption very and real time, so easily we can choose the source, choose the seller easily, right? Then it can control their consumption based on the real time pricing information. So the control can be automated also, and even possible via the web. So through the use of IoT, Internet of Things, we can also achieve this by controlling our consumption. Right? It is also possible. And also it can plug in, power electric. It can power electric and plug in hybrid vehicles, feed locally, generate energy back to the grid, and it can also feed the energy back to the grid. And what benefit it will give to the utilities? It will monitor the load in real time, anticipate demand, and automatically adjust the energy flows. Obviously, so it is important to monitor the real time load flow, and accordingly it can adjust the energy flow also to the network. Then peak load balancing, interact with the customers to reduce this demand at peak load. Okay. Enable integration of external renewable energy sources to pump electricity back into the grid. Okay, these are the benefits the utilities can get. Okay, fault isolation also one of the benefit. Advanced sensors allow quick isolation of faults in the network and speedy recovery, right? Then power plant growth, better management of demand and supply allows utilities to reduce need for additional power plant. Okay, now coming to the microgrid, as we have seen previously also, microgrid is an important component in the smart grid, because microgrid, uh, it is consisting of small areas where we integrate the renewables, small generators and controllable loads and energy storage. Now let us see, as per the concepts or definitions of IEEE, we can see the microgrid concept assumes a cluster of loads and micro sources operating as a single unit with control capability, which means it can disconnect from the traditional grid and operate autonomously. This is a clear-cut definition. So it is a cluster of loads and micro sources operating as a single unit with control capability. Okay. That means we cannot say always any type of load will take and we can say it is microgrid. So it should have control capability, and it can disconnect from the traditional grid and operate autonomously as well in islanded mode. Okay? And the microgrid can be powered by the distributed generations, energy storage systems, and our renewable sources like solar panels, wind power, fuel cells, biomass. So these are the components of generating unit which can supply power or energy to the microgrid. It provides backup for the grid in case of emergencies and enhances local reliability. So microgrid plays important role also when there is a blackout, and also it provides the emergency supply to the grid, right? So emergency supply means in case of power cut or in case of some contingency fault happens. So in that case, it provides power to the local area, and also it enhances reliability. And also during blackout, it helps to restore the system very well. It supports the system in the restorative process. So this is a technical report from IEEE which was published in the Power Engineering Society Winter Meeting 2002. It has a lot of citation. Now also it must have increased. So what are the key drivers for the microgrid? need for electrification in the remote locations and developing countries, especially in case of India and those are developing countries where there are many remote locations where no electricity reached even, only the only the poles are there standing, right? So in that case, we can create the microgrids. Uh, in fact, we submitted a proposal for Bihar rural electrification for creating microgrids. Somehow it was rejected, but in that proposal we proposed multiple microgrids which can interconnect it together and work together, but it was not worked anyway. So but it is very it can electrify the remote locations where electricity till now is not reached, right? And also transmission losses gets highly reduced. Obviously we know, because when at the load end we generate the power, the transmission losses will automatically reduce, right? And microgrid results in substantial savings and cuts emissions without major changes in the lifestyle. Savings in terms of cost, it will save substantially, and also it cuts emission without major changes in the lifestyle. Sometimes we force the electricity, because of the electricity we change our lifestyle. We know when the light will come, when the power will be resumed, accordingly we'll start our washing machine, start, right? So the lifestyle can be maintained without changing it. The microgrid helps this, right? Provide high quality and reliable energy supply to critical loads. So it is very essential. Critical loads means like nowadays we have a lot of data centers in many cities, right? Data centers are most critical loads which need always power supply, right? For those critical loads, it is very essential, and microgrid helps in maintaining the reliability to the supply to the critical loads, right? Now let us see the components of the microgrid. What are the components? Already we have seen there are three components: generator, load, and generator load obviously. Third component is energy storage device. It is essential because energy storage device maintains the stability in the system. Without that it is very difficult. Even if we'll see the case of the transmission power grid, in the power grid also they are putting big energy storages in order to maintain the stability, reduce the oscillation in the system. Recently in the northern grid they have put a very huge storage system around 100 megawatt, like that, very huge, in the northern grid, just to reduce the oscillation in the system and to maintain the stability in the system. So storage plays an important role. Therefore, distributed generation, loads, energy storage, and also we cannot ignore, last but the least, the static switches, which is very important role, which plays very important role in fact, right? That is the power electronic switches. That that plays very important role, right? Then obviously controllers we need. Then mode switching device, that is used in the uh, switching to different modes of operation. Then point of common coupling. Okay, point of common coupling where the microgrid is connected to the grid. Okay, that is the point of common coupling. So this is a typical microgrid structure we can see here, right? This is PCC where the microgrid is connected to the grid. Right? This is a typical microgrid structure where electric vehicles, renewable energy sources, storage, these are household equipments, everything is there, right? Now coming to the classification of the microgrids, most of the microgrids can be categorized into 5 categories, right? So what are they? One we call off-grid microgrids. Off-grid microgrid means it is not connected to the grid. So it is obviously, it includes islands, remote sites, where the electricity is not reached, and other microgrid systems not connected to a local utility network. So this we call off-grid microgrids. Okay. Next is campus microgrids, like our campus. Campus microgrid, where we have put 1 megawatt solar generation, and sometime also we feed to the grid when we in the off-peak condition in the night time, and not in the night time, during the vacation, during Sunday, weekdays, right? Weekends. So we feed to the power sometime to the grid as well, right? So campus microgrids that are fully interconnected with the local utility grid, but it is connected to the utility grid, but can also maintain some level of service in isolation from the grid. It can be isolated from the grid, such as during the utility outage. Sometimes suppose your outage happened, inside we can also supply the emergency supplies. We have some DGs also, diesel generators, right? And typical examples are the university and corporate campuses, prisons and military bases. Then community microgrids that are integrated into utility networks. Such microgrids serve multiple customers in service within a community, generally to provide resilient power for vital community assets. So this is community microgrid. So this is basically in a village, in a society we can make for supplying to maintain the resilience of the power to the community, right? And district energy microgrid that provide electricity as well as thermal energy. So this is a little bit different. Electricity as well as thermal energy for heating and cooling of multiple facilities. Like we visited Hong Kong in one of the conference, they took us to this kind of facility. They have created a district energy microgrid from where they supply the thermal energy as well to the nearby schools, nearby communities, right? So, so this is also possible, right? Then nanogrids, it comprised of smallest discrete network units with capability to operate independently. A nanogrid can be defined as a single building or a single energy domain. So this we can say a single house or building where we have various equipments along with energy storage and the solar system, wind generation even, right? So that we call nanogrid, right? Now coming to the operating modes of microgrid, where you can see here the microgrid is grid connected mode. There are two operating modes. One is grid connected mode and isolated or islanded mode, right? So utility grid is active in this mode and it supplies power to the microgrid, right? Energy to the power grid. All the feeders are being supplied by the utility grid. This is a typical structure we can see here, right? The point of common coupling, and here static switches, they are connecting. Here we can see here only the loads are connected. In this feeder there is no micro sources, right? There are no micro sources. Therefore it is a one-way power flow. But here there are bidirectional power flow. The power can be also transmitted from this side to this side to the utility, right? So therefore here we must have a bidirectional switch to transmit power from the microgrid to the grid, right? So this is a typical structure of grid connector microgrid, which is connected through the PCC, right? This is a bidirectional switch. So these are the renewables. Now islanded mode of operation, where the utility grid is not supplying power. Switch is open, okay, and micro sources is supplying power to the feeders, like here we can see here. Because this switch is closed, that switch is open, sorry, the switch is open at the point of PCC, and this is also open because there is no power flow from microgrid to the grid, and this is the feeder which is now off because no power is being fed to the feeder, right? Okay, so this is a islanded mode of operation where all the loads are being fed by the micro sources connected here in this, right? So this is a typical islanded mode of operation where power is flow. You can see here from electric vehicle the power is being transmitted from PV, right? From wind turbine. So these are the sources from where we are getting power, right? Wind turbine, PV, here PV, right? Electric vehicle. So let us discuss now the microgrid architectures. There are various architectures of the microgrid. So based on the connection of the sources and loads to the system and the configuration of AC and DC buses in the microgrid, the structure of microgrids can be classified into these three types. One is AC coupled microgrid, other one is DC coupled, and third one is AC DC coupled microgrid. Let us see what it is. Until now, the most used configuration has been AC microgrid. Till now, we are seeing most of the cases. But DC microgrid are gaining interest due to advantages they provide over the AC microgrid is no reactive power and no synchronization is required. Okay, these are the benefits we get from the DC microgrid, right? So therefore, hybrid AC-DC microgrids are raising as an optimal approach as they combine the main advantages of AC-DC microgrids. Okay. So you can see here the AC coupled microgrid structure where we have AC bus to which all the loads and the sources are connected. Even we have a DC distributed generation. It is also connected to the same bus to a DC-AC converter, right? So this is called AC coupled microgrid because the AC bus is being coupled with all the loads and sources, right? And also it is finally connected to the utility grid through PCC. Now coming to the DC coupled microgrid where we can see here we have, even if we have two buses, AC and DC buses, but the sources are connected to the DC. It is coupled to the DC bus, right? If we have DC load, it is connected to the DC bus, or else AC load can be connected through this, or else we have a bidirectional switch which is connected between AC bus and DC bus. The AC bus feeds to the AC loads, right? And finally, the AC bus is synchronized with the utility grid. These are taken from the reference 17 and 19. You can see it. So AC-DC coupled hybrid microgrid where there are two buses, DC bus and AC bus, both are coupled to the sources. So you can see here the sources are coupled to the DC bus, here it is coupled to the AC bus, and finally loads are being solved from both the buses, DC and AC buses, and only AC bus can be synchronized to the utility. So these are the three types of architectures. One is AC coupled, DC coupled, and AC-DC coupled hybrid architecture. Okay. Then what are the operating characteristics of microgrid? Before moving to the stability aspect of the microgrid, let us see what are the operating characteristics of the microgrid. Okay. So we can understand the diversification of microgrid structures because based on the requirement the microgrid structure is designed. So microgrid structure plays very important role in order to decide the operating characteristic of the microgrid, right? And also the grid connected mode or islanded mode, this is the mode of operation of the microgrid. This also plays in deciding the operating characteristic, which plays very important role in the stability study of the microgrid structure, right? And next is your voltage and frequency regulation, which also plays important role in the stability study, right? And your output impedance and overcurrent capability, this also plays important role. and the faster response and low inertia. Because we know the microgrids are consisting of power electronic switches. It has very less inertia as compared to the power grid or the utility grid. Because utility grid is connected to the synchronous generators, which is having very high inertia. Already those who have studied the power system, they know inertia of the generator or inertia of the system also. During power system stability, this plays very important role, right? If the inertia increases, the system becomes more stable. If inertia is less, your system is less. Even small disturbance, it will become out of step, right? It will become unstable. So therefore, microgrid has a faster response, but it has low inertia because it is not consisting of the synchronous generators. It is consisting of the inverter based. Most of the generators are inverter based, right? Inverters are connected. So therefore, this inertia plays important role. Therefore, it is always easy to handle the microgrid connected to the grid. That is, the grid connected mode of operation is better always. Better means in the sense it will make the system microgrid stable, because the high inertia of the utility grid will drive the microgrid. Okay, so therefore the stability is well maintained when it is connected to the grid. When it is isolated, the stability is hampered. It becomes less stable as compared to the grid connected mode, right? So these are the microgrid operating characteristics. Now coming to the classification of the microgrid stability. So already these classifications we have studied in the power system: small signal stability, transient stability, and voltage stability, right? Transient stability we know already, that is angle stability, right? This is the voltage magnitude stability. And small signal stability is, it is also angular stability, but it is because of the small disturbance. This is because of the large disturbance. Also, one more stability we study, we call it frequency stability. Okay, so that comes here, comes under the transient stability itself. So because of these aspects, this stability phenomena happen, right? So therefore we can see here, because of the small load change, because of the small signal disturbance, this stability comes into picture. And transient stability comes into picture because of the islanding, fault, right? Large load step change, right? Then loss of the generation. So these are the regions of happening of the transient stability. For voltage stability, we have reactive power limits, load dynamics, under voltage load setting, tap changes, right? Because of this voltage stability. So then how we can improve the stability? So in order to improve the small signal stability, we need supplementary control loops. We can use the coordinated control of DGs, stabilizers of DGs, and energy management system, right? So we'll talk about this little bit in the later slides. What is supplementary controller, right? And this coordinated control is not covered very much. And people are nowadays also working on stabilizers of the DGs, then energy management system. For transient stability improvement, control of storage, this plays very important role, and load setting methods, and protective device setting, control of power electronic devices, right? Then voltage stability improvement, obviously reactive compensation, load setting, modified current limiters, microsources, right? Then your voltage regulations with the DGs. So through these aspects we can improve the stability, various types of stability, right? So now we'll see the stability issues in the different types of microgrid. What are the issues in the microgrid? You can see here we have three types of stability here: small signal stability, voltage stability, and transient stability, right? And we have the different types of microgrids here. We can see here remote microgrid, campus microgrid, and utility microgrid, right? And we can see here, because of the phenomena, how these aspects in the utility microgrid can have these stability issues, voltage stability, small signal transient stability, through these phenomena, current limiters and tap changes and islanding fault, right? So because of this, uh, small signal stability, voltage stability, and transient stability, because of islanding fault, current limiters, and your tap changes, right? Similarly, for campus microgrid also, we have three transient stability happens because of islanding phenomenon, fault, loss of DGs, right? And also voltage stability happens because of the load shedding, limiters. Then switching, for load switching, small signal stability issues comes into picture, right? Similarly for the utility grid also, similarly for the remote grid also, we have different aspects which initiator which creates this stability issues in the microgrid, right? The stability issues are developed in the different microgrids because of these phenomena, right? Okay. So this is also taken from some reference, you can read it. Then coming to the small signal stability analysis, which one of our student working here. In fact, two students are working, Naresh and Asif, both are working on this small signal stability analysis. So small signal stability analysis is about the stability of the system when subjected to small disturbance. Okay, already we know this phenomenon in the power system, right? So one of the important concerns in the reliable operation of the microgrid is a small signal stability, because as I told, because of the low inertia most of the time, even the small signal stability issues are there in the large power grids, right? So because even if large power grids, they have the high inertia, small signal stability issues are there. Why not in the microgrid, right? Therefore microgrid has always the small signal stability issues, right? So one of the important concern is this small signal stability. So in conventional power system, stability analysis is well established on the basis of decades of experience. And because of the standard models, it is easy to analyze. Standard models of the synchronous machines, governors, excitation systems, and also even your uh, turbines, right? It is a standard model. Varying orders are known to capture the important modes for particular class of problem. And those who have studied the power system stability, they must be knowing that we have a standard model and we have different orders of model, right? And in order to capture uh, more transient phenomena, we have to increase the order here, right? Order of the model. And the simplest model also we can take to analyze for simplified analysis, right? To know whether the system is stable or not, just take the classical model, very simple model, we can analyze that through that. But for exact, if we'll consider the exact model, then more transient analysis we can do. So this doesn't yet exist for the microgrids and may be difficult to achieve because of the range of power technology that might be deployed. Because the microgrid, we know there are different kinds of uh, energy systems we are using, like solar, wind, right? PV is like your fuel cells. So and also gas turbines. There are many technologies are being connected, integrated, storage system. So in order to model the microgrid exactly, it is difficult because, and also the standard model still now it is not available. Like for power system, the standard models you'll find in the IEEE standard. If you'll see, you'll find it. But till now, for microgrid structure, we don't have any standard model for different technologies, right? So therefore, it is still a area where people are working. Uh, General approach for small signal stability analysis in the microgrid. So how we can approach for the analyze to analyze the microgrid stability analysis. So in the power system stability analysis, what is the general approach? What we do? The same approach will follow. What are the approach we follow in the power system stability analysis? First, because we need to have a model in order to analyze it, right? And that model, obviously, we make it through mathematical analysis, right? And that we call mathematical model. Through some differential equation, we develop those models, right? For all kinds of devices. So that is important to carry out complete mathematical model of the system, microgrid system. Those are the components in the microgrid system. We need to see those components and carry out the mathematical model in the form of differential algebraic equations, DA, right? So when it is done, next step is for small signal stability analysis. In the power system also we linearize the model. Why linearization is required? We linearize the model. Why linearization is required? Huh? Why we cannot do in the or exact mathematical model? Kundan, you tell.
Because in a small signal stability there is a small change. So the power and flux small change is look like
linear. Looks like linear. So any model, if there is a small change, small perturbation, for that the characteristics looks like linear, right? And if we'll took the linearized model, it is easy to analyze because it's a linear model. We can easily analyze it. The complexity arises when we will took the non-linear model, right? It is difficult to analyze the non-linear model. So therefore, even it is possible to do the small signal stability with the exact model, but it creates more complexity. So therefore, it is better to use the linearized model. So that linearized model should be around a stable equilibrium point. There may be equilibrium points that are unstable also. In power system also we have studied in the swing curve there are 2 points. One is unstable equilibrium point, other one is stable equilibrium point, right? Do you remember? Huh? So unstable equilibrium point we never take during the analysis. Always we take the stable equilibrium point. So therefore, always we should consider the stable equilibrium point during the formation, during the linearizing the model. Okay, and then form the state space model. In the state space model we develop from the linearized model, right? Okay. The next step is the system plant matrix is derived from that because the state space model, this is the cream, right? What is the cream? The plant matrix, right? From that cream uh, you can very easily observe the system, right? So to solve this matrix for eigenvalues, so that from the plant matrix we can find the eigenvalues, then load flow analysis can be performed to obtain the steady state operating points, right? The stability of the system is verified and then dominant poles are identified by performing eigenvalue analysis, right? This is generally we do in the small signal stability. Influence of the load line and control parameters are analyzed on the system stability and then the values are optimized, right? So these parameters are taken into account and what is those are having the effect on the stability and then those parameters are optimized. Okay, then validation of the stability analysis using the test system is it is essential for validating the test system, right? In order to test the stability, how it is working, right? So these are the general approach for the small signal stability in the microgrid, right? So through these approaches, anybody can do the analysis. And after that we need to implement some controllers. So this is the steady state system which is considered here. We have 3 DGs. You can see here. Those are the inverter based DGs. The DCs, DC generators you can say, or the energy storage device or the solar system, right? Which is connected to the microgrid through inverters, right? And these are the buses, the transmission line, and there are certain loads in each of the buses, right? Load 1, load 2, load 3. So this is the structure which is considered for the analysis here for the small signal analysis, right? Now this is the structure which is we can say after converting the transformation, right? Here we can see here this is 1 DG is considered for creating this control aspect, right? Not all other 3 DGs. 1 DG is considered. Here it is the grid, right? The point of common coupling. This is the transmission line. Here is a filter, right? So, and it is always easy to transform the ABC parameters to DQ0 transformation for the easier analysis. Already we do also in power systems, right? So by doing this, our analysis becomes easier by transforming from ABC frame of reference to DQ0 frame of reference. So after transforming, so these are the control loops we can see here. These are the signals VODQ and IODQ, which is fed to the power controller, that includes the droop controller. This is the external external loop, and this is the inner loop, right? So inner loop is your current controller and voltage controller, which maintains the current, and it gives the reference signal to the gate signal, right? Here you can see the reference signal is fed to the gate to create the gate signal for the switching device for the inverters, right? Okay, so these are the controllers. One we call the inner controller, which is current controller and voltage controller, and they are fed from the power controller, which is also including droop control. Droop control already you know. Droop controller we use in the uh, power system as well. In the generators we have droop, right? Percentage droop, you know, that is, we call it R, regulation, percentage regulation. That is because of the governor in case of generator, but here it is through a controller we are creating the droop. Okay, so that is so you can go inside this, you can study few papers, you can come into, you can gain the knowledge from this kind of structure, right? And this gate signal taking the reference signal from the current and voltage controller, it creates the gate signal for the switch inverter, right? Okay, so now we can, this is the structure, control strategy of the DG unit, basic control strategy. So with this control strategy we can go ahead for the analysis, right? So this is the little more elaboration of the power controller, that includes the droop controller. Here this is the filter. Here NP and MQ, they are the real power and reactive power droop coefficients, right? And they create the VOD dash and theta. They are fed to the current and voltage controller. Okay. So these are the equations, general equations derived from the mm, transformation, ABC transformation to DQ transformation, right? This is how we do the transformation, reference frame transformation, right? From DQ. So this is the equation we can see here, droop equations. This is frequency, omega. This is reference frequency. And NP is the droop coefficient, P is the real power. So this gives us the real power droop equation, and this gives us the reactive power droop controller D axis, right? Vn voltage, nominal voltage minus MQ Q, right? MQ is your reactive power droop coefficient, right? Now coming to the state space model. After deriving all those equations, from those equations we can see the complete state space model including outputs and inputs of the single inverter. This is for a single inverter, right? This is the state variable x dot inverter, right? This is your plant matrix A. This is a state variable. This is your output matrix, right? So then also we have a algebraic equation here. This is your differential equation. This is your algebraic equation which includes the omega and I naught, right? Similarly, corresponding states of each inverters. So each inverter, the states are this: delta, P, Q, and phi. All these are the states, right? So these are the plant matrix, output matrix, right? So general state space model. So finally, these are the state matrix, and so you can go through the papers. Already, I think Norris has published one paper in Access, IEEE Access. You can go through that. The detailed model is there. So this is the combined model of the three inverters. I have shown the single inverter. Then after combining the three inverters, you'll get the combined model. Okay, this is the algebraic equation. This is the differential equation. Okay. So this is your A matrix for combined inverters. All the inverters combined together. This is a diagonal matrix, right? You can see. So this is B matrix and C matrix. So and then we need to add the modeling of network and loads. Okay, the modeling of network, similar way it is done. This is the current in the line and this is the load current. Okay, then it is the complete microgrid model including all the inverters and line. Okay, these two equations gives us the complete microgrid model. These are the study system parameters considered during the analysis. Right? These are the parameters LF, RF, CF. They are the filter type parameters. LC, RC. They are also filter parameters. Okay. And omega and Vn, NP, MQ. They are the parameters, basic parameters taken from some reference, and they are used here. Okay. And we need to see the effect of these parameters, the variation of uh, the eigenvalues or eigentrace by varying this NP and MQ and other parameters. So these are the initial conditions taken from the load flow solution. Those we call it the stable equilibrium points, from where we considered the from where the linearization took place and the model is prepared, right? So this we call it the stable equilibrium point solution, load flow equations, right? Okay. Now we can see the traces. Few figures I will show. These are eigentrace. We can see here the trace of the eigenvalues by increasing NP and by increasing NP here. We can see here how it is passing, going through, right? So here trace of the dormant load locus as real power droop coefficient NP is varied from 1 e to the power minus 6 to 2 e to the power minus 3. So at 2 e to the power minus 3 system leads to oscillatory performance. Okay. So here if you see the axis, here it is 0 axis, this side is negative. So all this side is there, this indicates they are stable modes, right? And as soon as it touches the imaginary axis, oscillation starts, right? Okay, so therefore at 2 e to the power minus 3, when NP is equal to 2 e to the power minus 3, it becomes oscillatory. That means at this, it touches the axis here, right? So that means these are the critical values. This value is the critical value of NP where it starts oscillating, right? Your system. So now this is the locus, trace of the root, trace of the eigenvalue. As the reactive power Drude coefficient MQ varies, right? As MQ increases, right? Here and here it goes. So at the point here touches the imaginary axis, right? So that means this gives us the oscillatory mode. So this is the effect or impact of varying MQ and NP both, right? And here also at this point we call this MQ as the critical value, right? So these are the effect of KPV, which is the gain constant for the power controller, right? For the current voltage controller, right? So this, as it is varying, right? So it also varied and the trace was found. This also, from here also some critical values found, right? This is similarly KPV dash. This is another gain constant. KIV dash for current controller, right? KPC, then your, these are the, all the effects have been studied and the critical values were found for all the constants, right? Now we need to optimize the parameters. We found some range of parameters, the critical values of MP, NQ, KPV dash, KIV dash, KPV, KPC from the eigenvalue analysis, and which is the best value out of those range. So it can be found from the optimization. So here the optimization is PSO algorithm is used, and the objective is minimizing the difference of power, both real and reactive power. Okay, PM minus P reference and QM minus Q reference. So overall objective is minimized with these constraints, right? So these minimum and maximum values we know from the eigenvalue analysis. From that it is decided, right? Then after optimizing, this is PSO algorithm convergence. After optimizing, these are the optimal values found for NP, MQ, KPV, KPV dash. So these are the optimal values found from. Okay, now those are the basic controllers used, like PI controllers for current and voltage controller. Here one more controller is analyzed, that is the IMC based Drude controller. So for that also similar uh, process flow was followed, right? So for IMC controller also it is found this is the complete eigenvalue study, and gradually this is the magnified part, and here the comparison is given for PI, IMC and proposed. Proposed controller is your IMC with optimization. Okay, so that is the proposed controller, that is IMC with optimization. Right. So this is the disturbance given during simulation, and we can see so the disturbances are given in the steps from 0 to 1 second, then 1 to 2 second, 2 to 3 second. There is load change gradually from, these are the sequences how the load change happened in load 1, load 2, load 3, and certain disturbances also injected, right? So in order to evaluate the effectiveness of the optimal IMC based Drude controller, that is IMC plus optimization, optimizing the parameter, right? The disturbance is in the form of step load is applied during interval from 0 to 1. So the optimal control value is evaluated with PI and IMC based controller. For both PI and IMC it is also evaluated. Now in the time domain simulation we can see the impact of these controllers. One is your PI controller, IMC controller, and proposed. Proposed is the optimal IMC, which is IMC plus optimization. Okay, that is where the parameters are optimized, right? So from the figures we can see the best performance is by the proposed controller, which is IMC plus optimized, or we can say optimal IMC controller, right? IMC is internal model control, right? That is IMC control. So we can see the curves and compare. From this comparison we can find this, that IMC, optimal IMC gives the very good result with less transient rate and very smooth uh, transition. So this is for real power. Okay, real power for all the three DGs it is shown, right? Then for reactive power also it is analyzed, and it is also found the same, that the proposed controller giving good analysis. You can see here this part is magnified. Here we can see the blue curve for DG3 and DG2, right, for DG1. So the smooth transition, right? So therefore, and without any more oscillation or transient. Also very less overshoot. There is no overshoot at all, right? So this is for reactive power. Now coming to the D-axis current for both for PI controller, for IMC and proposed. Okay, here we can see the oscillation for PI controller, and for IMC also there are little oscillation as compared to PI, but in the proposed controller it is very smooth, right? So therefore proposed controller is fine for the this analysis, this microgrid structure, right? Isolated microgrids. Now this is one more Q-axis current response for all PI, IMC and optimal control. You can see it later in the side, in the PPT will share, you can see it. And also will you can see the references, from the references you can see. Okay, so this is another for filter current response for DG3, DG2, DG3, DG1, DG2, DG3, right, for all the three controllers, right? Similarly for Q axis filter current, and then it is D axis output voltage. Okay, in all cases we found that the system is behaving good for proposed optimal IMC control. Okay. So this is analysis, as I mentioned earlier. This is a detailed analysis of small signal analysis and the controllers we use, right? Now we'll little bit discuss about the protection, then we'll stop. Okay. So what are the protection challenges in the microgrid? In the power system also, in the protection, there are different attributes. Various attributes we cover, right? So those attributes must be fulfilled when the protection system is designed. I think Dr. Joe is covering more about protection in the next class, in the next lecture when he will be giving. So the attributes generally selectivity, then sensitivity, reliability, right? These are all attributes, and these attributes must be very well fulfilled when we are designing a protection system. And in the microgrid, there are various challenges, because when we are designing for a distribution system, normal distribution system, the power is flowing from one way, right? It is the passive distribution network from source to the load. The power is flowing, and it's one way simple overcurrent relay you put. It will give us a very good design, right? But here, what are the issues? The first issue is variation in the short circuit level. Short circuit level means the short circuit current, it varies always in the microgrid for different operating modes. Unlike the grid or normal utility grid, right? So how it varies? So with the addition of DG, the fault current is being supplied by DG and medium voltage grid both. So when it is in the grid connected mode, suppose a fault occurred, so the power will flow from that side, the current will flow from that side, grid side, and from the generation, from the DGs also, right? So therefore overall current, if we'll see, it is significantly high. in the grid connected mode. And under isolated mode it becomes less because grid is not connected, only DGs are supplying, and it is very less as compared to the grid connected mode, significantly less the fault current. So therefore the setting in the relays we need to adapt. Therefore adaptable setting system is required, right? It means it can adapt to the both grid connected mode and operate and isolated mode, right? And another problem is bidirectional power flow. So bidirectional power flow, it also in the relay setting it creates problem, right? Though we can use the directional relays, but still it creates problem during fault, right? Because of this operating modes, for different operating modes. So you can see here, this is a passive distribution grid, right? Where if the fault occurs, if it is grid connected, obviously the direction will be different, and in the isolated mode, the current direction will again be different if the source is not here, right? Now coming to here where uh, a microgrid system, the active distribution grid, right? In that case, it will be the scene will be completely changed. The power is flowing from different direction, right? So it will have a different issue, right, in the protection system. And the third challenge is fault current contribution based on the DG type. So there are different types of DG used: synchronous based, inverter based, right? Storage, right? So therefore microgrid operates with two types of DGs: synchronous and inverter. Synchronous based are usually low inertia machine. Usually they contribute up to 5 times the rated value of fault current. But due to limited current rating of converters, inverter based DG contributes less towards fault current as compared to the synchronous DG. So intermittent power output of renewable based DGs, right? This is the fourth point where the power output from the renewable energy source, it becomes intermittent, right? So sometimes it is very less, sometimes it is high, right? So if the storage is not there directly grid connected, it has a different issue also, right? So due to large number of converters present in the microgrid, current and voltage harmonic prevails, which affects the conventional protection scheme. Harmonics plays very important role. So because of the harmonic also, sometimes large magnitude of currents, because of that harmonic, it causes, it is seen by relay as a fault current, right? Like I'll give an example of transformer harmonics, the magnetizing inrush in a transformer. That also that also is seen by the relay as a fault current, because but actually it is consisting of many harmonics and DC components, right? So therefore in transformer we put the harmonic restraint percentage biasing relay, right? So in that case the harmonic is due to the harmonic current, the restraint is created, which doesn't allow the the differential relay to operate during the magnetizing inverse. Similarly here in the microgrid we have many inverters that creates harmonic, and during fault also it will have harmonics with higher magnitude. So that has to be taken into account. Okay. And next is unwanted tripping. False tripping occurs when the fault current occurring in a feeder is supplemented by the fault current generated by DG in a neighboring feeder attached to the same substation. So protective equipment of the neighboring feeder might disconnect the circuit. Okay. So this is unwanted tripping. Then blindness of protection, and this is a pickup current is configured in a way that is more than rated current of the feeder and less than minimum short circuit current. So when DG is installed to a network, the feeder equivalent impedance is increased. So that creates the blindness to the relay. So it cannot see the exact fault current. The prohibition of the automatic reclosing with addition of DG radial network, the radial nature of network changes. However, the reclosure disconnects the MB network. DG still supplies the fault current. Okay, so whenever there are automatic reclosure, the for temporary faults, there are reclosure switches. So when any fault happens, the circuit breaker trips, and again it recloses. It is in practice it happens. It doesn't identify all the fault as permanent. The permanent fault will be identified only when the reclosures fails 3 times or 5 times, something like. In the distribution system, it is 3 times. In transmission system, it is 1 time. When the reclosure fails, right? This is how reclosure affect. When the reclosure is still, it is reclosed, right? So that time also this kind of issues takes place. So there are possible conflicts between feeder protection and fault ride through requirement. Okay. So fault ride through means the fault may happen outside the microgrid in the distribution system, and the relays connected in the microgrid, it will see that the fault happened inside the microgrid. That is fault. That is the effect of fault ride through, right? So that creates conflict whether the fault is inside or outside, right? So then, what are the protection schemes available? Basically, we can say the microgrid is a distribution network where we use, generally in the distribution network we use the overcurrent relays, right? Sometimes it is the bidirectional relays are used, sometimes only overcurrent relays based on the requirement. But here in the microgrid, obviously we need a directional overcurrent relay, right? So most of the economic relay is in the distribution level, because this is the overcurrent, simple overcurrent relay. To overcome the bidirectional power flow issues, directional overcurrent relays are used, right? Since the fault current level is much lower in the islanded mode as compared to the grid tied mode, the overcurrent relay settings must be updated based on the mode of operation, right? As I told, in the different mode, the current level is different. Therefore, the relay setting must be adjusted based on the mode of operation should be identified. Based on that, the relay settings should be adapted again, right? It should be adjusted. Because in the numerical relay, it is easy to adjust. Automatically, it can be adjusted. Offline calculation can be done by solving relay coordination problem. So, offline offline design of the protection schemes is possible for relay coordination. This is one of the work by one of our student, and also here Jayant Murni is here, right? He is also one of the co-author. So this is published in IEEE transaction industry application, right? This is a simple offline protection scheme for the microgrid, but only it uses a optimization technique, that is gravitational source technique, which is compared. There are different cases has been considered for the design, and for different cases are also different different comparisons are made with different optimization technique. So here the objective function is to minimize the operating time of the relay, right? So this is the another type of scheme, we call it communication assisted adaptive protection, where as I told, the settings should be adjusted based on the operating mode. So therefore, this is a kind of the scheme where communication schemes are used to change the setting in an intelligent way, right? So by extensive calculations, once the relay settings of both mode are calculated, online update can be done. This requires numerical relay that can operate on more than one overcurrent characteristic. Okay, so there are many characteristics for overcurrent relay. Okay, a normal, inverse, very inverse, extremely inverse. So different characteristic should be there because it is available in the numerical relay. It can adapt for different types of operating modes. The communication links and intelligent IED also used and it is done in the central protection computer protection center, where it is done, and the signal is again sent to the uh, relays, right? You can see here from relay 3 the signal is sent, the information is sent to the central protection system. Again here the operating mode is identified, right? And accordingly the relay setting is updated. Okay, this is called adaptive protection, where we are using the communication techniques. So adaptive protection coordination is an online activity to change the settings of DOCR, that is directional overcurrent relays, in order to provide better coordination and selectivity with prevailing power system conditions, right? So it would require use of bidirectional and digital overcurrent relays. Digital overcurrent relays should have group settings. These group settings are changed locally and remotely. Usually, high speed and secure communication facility is required. Generally, optical fiber network is chosen for this communication link, right? And there are different types of adaptive protection schemes. One is centralized, other one is decentralized adaptive protection scheme. Okay, decentralized means at different nodes we have the computers or the computational devices which can get the information and give the signal. And centralized means we have a central protection system where all the informations come and they give the signal. There are few advanced technologies which use the energy storage devices. This is a source of fault current when islanding. This would maintain the fault current. Considering this ESD and digital relay activation using more than one logic, right? So there are few advanced techniques. You can see it also, and some machine learning techniques also nowadays used, and some data analytics techniques are used to create a adaptive protection system, right? Okay, so we'll more talk about machine learning and data analytics in our later classes. Those will give the basic idea of machine learning and data analytics. Okay, so this is the fault type distinction, where the SBM is used, fault location, finding the fault location also, right? So let us conclude our session. So we discussed different topology and control schemes of AC/DC microgrid, and also we discussed various structures, right? Then we discussed the small signal stability analysis with IMC based group controller, and also we discussed with optimal IMC group controller, right? Then we observed the system stability, small signal stability, that is highly sensitive to specific control parameters, and they play a crucial role in the reliable operation of the system. The critical values of these parameters are determined and the stability domain is formulated. Parameter optimization is done using PSO rate. So these optimal control values are used to improve the dynamic response under different operating conditions. So okay, so then the effect of key parameters are validated through time domain simulation. It is through the MATLAB and Simulink, and it is observed that it has a significant impact on improving the stability and dynamic response of the system. And finally, the proposed optimal scheme based on the small signal model, which is we call it the IMC, optimal IMC, right? That gives the substantially good results, right, in terms of transient and steady state response. And also we discussed issues related to the protection schemes in a microgrid and how it is important the adaptive protection system is for the microgrid. And also we concluded that the adaptive protection scheme can be implemented very well by using data analytics and AI techniques, which the basics of which we'll cover in this course. Just okay, thank you very much. These are all references. You can See these references all about the microgrid stability, control, and protection. Thank you very much.